Good morning.
Good morning, sir.
Yeah, so I think the last class we covered the second unit, that is enhancement, which is done both in spatial domain and also frequency domain. We also saw various sharpening filters and smoothing filters, both in spatial domain and frequency domain. What we understood is image enhancement technique actually tries to improve the image for a better perspective view of a individual. Uh, this class, let us start a new unit that is on image restoration. Okay, is the slide visible?
Yes, sir.
Okay, fine. So third unit is image restoration. As the name itself says, you are trying to restore the originality of an image, which probably would have undergone some variations or some degradations. Okay, so this particular unit we are going to cover the basic definition of image restoration. That means, what do we mean by image restoration? Uh, we develop a model for the degradation that happens whenever I capture an image by using a camera. There are several, in fact, degradations that might happen during the acquisition process. So we will model that by using a typical process. And once we model the problem, then we try to do an inverse of it. We call it as restoration process. Now, since noise is one of the degradation that is expected usually when you acquire in fact, image, or when you are transmitting an image from one place to other place on a channel. So we discuss what are the various noise models that are normally used in image restoration, and then we start solving the problem by making some assumptions. The first assumption we make is we assume that the image is corrupted only because of noise, so we try to restore it only in the presence of noise. Then we assume that there is only blur, the degradation is blur, and model it and perform an inverse operation of filtering. Thereby, we obtain a restored image. And there is a specific type of filter called Wiener filter, which is an advantage over an inverse filter. We'll discuss it, and we will extend that, and we also try to learn about constrained least squares filter. Okay, so these are the topics that we are going to cover in this particular unit. Okay, now whenever you want to know something about a new word, the first thing that we do is we'll just try to search in Google. So when I did that image restoration, when I gave that as a search, actually one of the link that I got is something called image restoration theory. Um, but when I went through the details, hopefully you can read the details here. So actually this is in fact in no way connected to what I'm talking about, because this image restoration theory, it is actually outlining the strategy that can be employed to mitigate damage to image in an event where reputation has been damaged. For example, a well-known person, a very important person, a VIP, because of some maybe issue, probably his or her image would have been spoiled. So there is a theory where we can, in fact, uh, restore the image of that but individual person. Okay, so why I wanted to show this, because normally I have seen when questions are given in the test or quizzes, you try to use Google and try to okay get the answer from there. but sometimes it may not be relevant to what you are looking for. This is no way connected with what I'm going to discuss in the next few slides. Okay. Okay, so there is one more image restoration that normally you see when you go to photo studios. In fact, uh, uh, suppose if you have a good old image, maybe of your great grandfather or great grandmother, whose only image print that you have, don't have the digital version of it, but you only have the print of it. Sometimes it's quite possible that the image is spoiled because of maybe some water falling on it or some paint on it, or maybe the print is torn out. For example, in this case, you can see there is the image is completely spoiled. So there is some, in fact, variation here. What these photo studios will do is they will try to restore the originality. They'll just undo those effects. For example, in this case, this is a damaged image or a degraded image, whereas you can see these scratch marks and all that are there on the photo, they have removed it. Similarly, some okay problem here, and also the image looks very dull, maybe because of dust falling on it. So after I restore it, I'll get a better image. So this is quite possible. In fact, if there are some probably cases where you don't have the digitized version of the image. In fact, a good example that I can give is this photo. Okay, uh, are you able to see the photo?
Yes, sir.
Okay, actually, this is the group photo when I was doing my SSLC, that is my 10th standard. Uh, so somehow through my in fact classmate, a 10th high school classmate, I could get a photo which he had preserved it. That means the hard copy. But unfortunately, this is what has happened. So the question is, if I want to preserve it, if I want to restore it, is there any way I can remove it? You can see there is a way. For example, these cases, there is a way you can actually try to undo the effect. So so that is exactly a challenge, and in fact, Photoshop or Photo Studio people they actually do this many times. At least I have experienced. Maybe my great grand father, okay, photo which we don't have. So normally they'll take an old photo which will be scanned, and any such variations they'll remove it and try to give you the original image. Okay. Unfortunately, I could not restore this image because it's not an easy thing. But this is just I wanted to share an example. So this can also be called as image restoration, wherein you just try to remove these types of variations on the image, maybe color dimness, or maybe some scratches, or maybe some breaks. You just undo it so that I'll get back a original image. But let me tell you, this is also not what we are going to do. This is what Photoshop Studio people will do. So we are not doing this. Okay. What actually we are doing in this particular unit is the following. Can somebody tell me what is the problem with this type of this image? What do you think is the effect here?
Sir, motion blur, maybe.
Yes, very good. Who is it?
Sir, Swami.
Soumya, very nice, very nice. So you can definitely see that there is a blur because of some motion. Uh, So, uh, what happens is I'm probably when I'm having a camera on a vehicle and the vehicle is moving. So when I expose a scene, depending on the exposure time of the camera, the time that it takes. So obviously, it is going to average the variations in the scene and give me some pixels. So when that is happening, if there is a still photo that we have taken and there is no movement in the scene, the camera is also not moving, then obviously we'll get a very nice image. But when there is a motion, which is obviously true, for example, when I'm using camera for traffic surveillance, you cannot expect the vehicles to be stable. They will be moving. So obviously you can expect that there is a blur that is going to be there. So what you see here is a motion blurred cameraman image. Okay. So what we try to do in this particular module or unit is how do I reconstruct the original image? That means a de-blurred image where this blur has been removed and you could get a very clean image, or I don't say clean image, it's a restored image, the original image. And this is a requirement because you cannot expect that you just have a look at the image. If it is not properly captured, you do it again. Normally when you go out for a picnic, you do that. You just uh, take the snapshot and you will observe that there is some blur. So what you will do, you will again take it. But in satellite imaging, when satellite has captured an image, you cannot expect that the satellite to come back to the same place and again capture the image. In traffic surveillance, you cannot expect the vehicle to stop so that you will get a better image. The vehicle will be moving, but I need to take the image. If there are any such changes, I need to restore it. So with this background, let us now define what is image restoration. Every word in this definition is important. Image restoration attempts to reconstruct or recover an image that has been degraded. Okay, so the degradation could be the blur like this. There is one more degradation called the noise. I hope you remember when we were doing image enhancement, we talked about noise. Can you tell me one type of noise that we uh, talked about? An example? Can somebody? We removed it by using median filter. Anybody? A type of noise which we removed by using median filter. Anybody? Quick answer I want. Impulse noise. I think Rakshita is typing in impulse noise. Very good, Rakshita. So impulse noise, in fact, salt and pepper type of noise is an impulse noise. So we removed it. So any image which is degraded because of blur or noise, we are going to reconstruct or recover the original image from that, and that is called image restoration. But what is important is we should have some a priori knowledge of the degradation phenomena. That means I should know how the image is captured. For example, in this case, Saumya, I think he told this image is a motion blurred image. So if I know that an image is captured whenever the camera is moving or when the scene is moving, then it would be easy for me to model it and then restore it. So a priori knowledge of the degradation phenomena is very much important. Okay, let me give an analogy. Suppose if I have any medical issue, I have some problem. What is done actually is I'll go to a doctor. So the doctor will not just look at me and say, yes, you have this problem, take this medicine. I don't think anybody can do that. If I just go and sit in front of a doctor, you cannot expect doctor to just identify the problem and then give medicine. Then he should be called as a god. A doctor cannot do that. So what doctor will do? He will say, so what is the problem? And we will start giving the okay symptoms. So I'll say I have some problem. For example, I say I have some problem maybe near my chest. Okay, so then doctor will ask some more questions. Okay, so do you have any family history of that, or uh, do you have any previous such type of pain that you have experienced, or the doctor may also ask me, uh, what is that you ate in the last 1 or 2 days. That means what was the food that was consumed, because he wants to just model the problem. Means he wants to know why is this pain. Just because I just mention that I have pain near my chest, you cannot say that it is because of maybe some chest pain, maybe heart problem. So you have to undergo some surgery, or so. No doctor can take a decision like this. So he will model the problem. He will just try to ask so many questions. Then suppose if I say maybe in the previous 1 or 2 days I ate some junk food, like some uh, food that street food that we normally should not do. So he will say, yes, maybe there could be some problem with gastric type of problem. So he will probably ask me to go for maybe some further investigation. So first he should identify the problem. If the problem is properly modeled, then he'll try to do the inverse. That means he'll try to give something which reduces the gastric problem, and probably my original health will be recovered. Okay, I intentionally gave this analogy because it is going to fit your definition now. So what is required is a priori knowledge of the degradation. That means how I got this health problem. If this is given to the doctor, then the doctor can restore my health and give back my original health, or at least very close to my original health. So there are two steps in restoration. What I said, one is you need to model the degradation process. That means how the image is captured. Have I captured an image when the lens is not properly adjusted? Have I captured an image when the camera is moving? Have I captured an image where there is lot of lightning and maybe rain, thunderstorms when the image is captured? This can happen in satellite imaging. So I should first model the degradation process and then try to apply the inverse process. Okay, do the inverse so that I can get back the original image. Okay. Now you may ask me a question, what is the difference between image enhancement and image restoration? Because there also to some extent we discussed about improving an image. Okay, here also you are trying to do the same thing. Now just see these differences, very important differences. Usually image enhancement is done for better visual representation. Remember, there was a low contrast image, so you just did the histogram equalization, the contrast improved. That means it is used it is done for better visual representation. Whereas restoration, it is specifically done to remove the effects of sensing. That means while capturing or while acquiring the image, you would have experienced maybe some blur because of motion, or because your camera is not set properly, or there could be noise that gets added because of your camera itself, or maybe because of your environment at which you are taking the image. So one is done for better visual representation, other is done for removing the effects. Okay. Now in image enhancement, when I just did the histogram equalization, I only asked you which image is better, and many all of you said that the second image is better after a histogram equalization. So that means I asked you a question. I just said which is better. You said something is better. So it is subjective. What good looks good to you may not look good to some other person. So it is subjective. Enhancement technique is subjective, whereas restoration is objective, because the very clear objective in restoration is I should remove the noise, I should remove the blur and give you a clean image. That means a restored image or a degraded image. A, a, a good image which doesn't have any of these degradations. Okay. So enhancement is subjective and restoration is objective. The third difference is when I said hedges are improved, remember we did edge crispening by just adding original to the Laplacian. I hope you remember these topics that I did. When I said, when I showed you the output image, you only observed that the edges are improved. That means the edges are looking better. But I cannot quantify. That means I cannot say how many edges are improved. Also, if I improve the contrast, I cannot say what percentage of contrast improvement has taken place. That means I cannot give a figure, a number. That means we don't have any quantitative measures. Whereas restoration, there are measures. Depending on the model that we are using, there are measures. For example, I can use in fact, something like signal to noise ratio. So I'll just show you what is the signal to noise ratio prior to restoration, what is the signal to noise ratio after restoration. So there could be improvement in the signal to noise ratio. That is one of the uh, measure. Or I can say mean squared error. I can just compare, just tell you what is the mean squared error. So I can give some quantitative measure, whereas here there are no quantitative measures. And enhancement is a heuristic process. Nobody told you that first use image negative, then use image logarithmic transformation, something like that. You had to apply the technique, and then you had to decide whether it is doing good to me. Where there is a spelling mistake here, please correct it. This is knowledge. Um, Restoration depends on a priori knowledge. That means what is the degradation that has taken place, and depending on that, I do restoration. In enhancement, I don't say the input is bad. See, it is a low contrast image. I cannot say it's a bad image. Okay, but it is not good for my application. That means if I am just trying to have a better view, or I want to do a better segmentation, contrast is very important. So I for me it is not good, so I cannot say it is bad, but I want to improve it. Whereas in restoration, the input image is really degraded. For example, in this case, this is a bad image, this is a degraded image, so I need to improve it and give a good image. Okay, so now let us try to model the problem by just taking care of what is the input and what is the output, and how what is the requirement. Okay, so in the image restoration, as you all know, I have a degraded image and I want a clean image, or I have to recover the original image from that. Now, so input to my restoration block is a degraded digital image. Okay, something like this. It's a degraded, that this should be the input and this will be the output, and the output will be a restored or a cleaned image. Okay, now notice here the some things we are not considered while doing it is, there could be some problem with the display itself. So I am improving an image, I am not looking at where it is being displayed. I cannot take care of the display degradation, so it is not considered here. While digitizing, there could be some noise that is introduced, or such type of quantization noise or digitizing noise we are not considering here. Sensor which is introducing noise, we may not consider it. Okay, so these are some assumptions. Now what is important, as I already told you, is that is the definition: a priori knowledge of the degradation phenomena. So one has to have some a priori knowledge about the degradation process. So that means I should know how the image is captured, how I got this type of degraded image. This has to be known. I repeat again, is it a traffic surveillance image where the camera is kept at a particular distance and the vehicle is moving, because of which there could be some motion blur? Not only that, the image is captured when there is lot of rain at that particular point of time. So depending on that, we can just model the problem. So prior knowledge about the degradation process is important. Now the next thing is, when I give you such an image, where I say input is a degraded image, I should know what is the noise. Noise, you cannot just simply make some assumption. So you should definitely know what type of noise is there. So that is why we need to discuss about the various models for noise. Then the next thing is, we should have a model for degradation. That means how the image is captured, what type of degradation has happened. Is it motion blur? Is it something like defocus type of blur? Is it salt and pepper type of noise? Is it Gaussian type of noise? So we need to know about the degradation and model it. We need to know about the noise. In fact, we should also know something about the original image. That means some information about how was the original image. Okay, so because if this is known, whenever I do in a restoration process, I can compare my result with this original and say I have done a good job. Okay, so as usual, just like in image enhancement, here also there are two approaches. One is spatial domain, other is transform domain. as usual, there are two approaches. So either I can perform restoration in spatial domain, or I can perform restoration in transform domain. Okay. Now this is the model. Okay. So this is a model which we actually developed for degradation and restoration. And if you understand this, I think uh, in fact the problem could be well addressed now by using some techniques. Okay, so just keep looking at this model. I'll be back in a minute. Give me 2 minutes. Okay, I hope uh, probably would have understood it, but still I should explain it. Okay, can anybody okay, just explain what is the meaning of this? Any can somebody try before I explain it? I'll just ask a specific person. Okay, Pramod NR, are you there? Pramod.
Yes, sir.
Okay, can you just make a try? What I am just trying to uh, explain here. What is the meaning of this? Just
Actually,
make it.
given the input image
Yeah. So
degraded function.
I have an image here. Okay. What is this effort? I think everything is written here. So there is a scene that I am capturing. Okay, there is a scene that I am capturing, or this is the input image, the actual scene that the camera is looking at. But because of some variations, okay, some degradation is included here, introduced here. The As I told, the basic degradations that we see is a blur and noise. So the model now goes like this. There is some blurring that is happening. This could be because there is a relative motion between the camera and the scene. Maybe a vehicle is being captured by using a still camera. So vehicle is moving, there is a relative motion, or vehicle is still, the camera is moving. Maybe some other situation where you are on the camera is on a moving vehicle and you are capturing some other scene. So there is a motion, or your camera is not set properly, that means the lens is not set properly, so there could be some blur. We call this as defocus blur. So the image f of x comma y, which is the original image or the clean image, it has undergone some blurring, which we call it as degradation function h. Okay. Then I also said during the acquisition process, there could be some noise that is getting added. Assume that the camera is fit in a traffic point and there is severe rain at that time, and you are capturing the image. So obviously the image is captured with some noise. Okay. So the degraded image here, that means the blurred image, gets added with noise. So what you actually have captured is this. Okay. That is your g of x comma y. In fact, this is the image which is degraded. F of x comma y is your input scene or the clean image or the input image. There is some blur that is happening. The blur is represented as a black box here. We call it as a degradation function h. And there is some noise that is getting added. Okay, eta of x comma y. So your g of x comma y is a function of this blur function and the noise. So G is a degraded image. Okay. So this is the model for degradation. What is the model I have used? You have to carefully observe. I am assuming that the blur function is a black box. Okay. It is just like a system where it takes some input and gives me some output. The input is a clean image. The output of this system is a blurred image. Okay. And I am making one assumption here, this plus sign. So this is an assumption in my model. That means I'm just telling you that the noise is getting added. Okay. Noise can be multiplied, can also get multiplied, but we are making an assumption that the noise is getting added. So your G has come because of this degradation and this noise. So this is your degraded image, which is this. Okay. And what is your objective here? You as an image processing expert should inverse it or should restore it and give me, in fact you should give me f, exactly f, but most of the time I cannot get exactly f. I'll get f hat or f cap here. That means I'll get an approximation to f. Okay. Even in the analogy I told you, you cannot expect every time when I go to a doctor I'll get back the originality of my health. For example, if it is say a severe heart disease, no doubt because by using some angiogram, some angioplast, okay, they will put some stent and they will make you in fact active. But do you think that I can work again with the same pace what I was doing before this heart attack? No. They would have all definitely have told you that you cannot take some specific type of food and you have to have okay, rest, take rest. You have to take specific medicine every time, which means that I'm okay, I'm good, but I may not be same as what I was prior to this heart attack. I hope you understood that why I told you this analogy, because what I get here, the restored image, I cannot say I'll get back the exact original. Okay. For example, when I showed you the noisy image and then removed noise by using some filter in previous chapter, the output, no doubt the noise was removed, but do you remember something else happened? Can somebody tell me what is that happened? When I tried removing noise, something else happened. What was that? Anybody? If you cannot speak, you can chat also. You removed noise, but that is at the cost of something else. I told you this. Anybody? Okay, I'll take a name. Ramya, yes. Ramya. If you are not unmuting, I'll assume that you are not there in the class. Either you have to unmute and speak or you have to chat.
Yes, sir.
Ramya, what is the effect? When I I removed salt and pepper noise or maybe any other type of noise, but you saw something else. I showed you clearly during the class. No idea? No, it is not ringing effect. Sindhu is telling it is ringing effect. Uh, yeah, that is because of the filter, but uh, something else also happened. So for example, when we saw that image where you had alphabets, no doubt the noisy region was removed. Double edge effect, no. These are all effects of your filter. I am just talking about on the image something happened. Okay, I'll give a hint. What was the effect of a smoothing filter on edges? Yeah, blurring. I think Rakshita is correct. So noise was removed, but that was at the cost of blurring. So which means that when I try to restore, assume that this is a noisy image, and I apply a simple smoothing filter, which could be a mean filter, that is a box filter that I explained in the previous chapter. I got an output image, no doubt, where the noise was removed. That in that way, it was this image is very close to the original image, but I cannot say it is exactly same as the original image. The edges were blurred. Okay, good. At least somebody is answering to the question. I'm happy. Fine. So f hat would be very close to f, but I cannot say f hat is exactly equal to f. It is very rare that I'll get back f from g of x comma y. However good I am in restoring, I would definitely cannot reach the original image. So the efficiency or the capability of your restoration algorithm is decided by how close I am going to f. That means what is the error between f and f hat. So the lesser this error, I say the efficient is the restoration algorithm. So the whole of our challenge is how good I can restore so that I can go very close to the original image. So now I think the concept is clear here. So F is the input image, G is the degraded image, N here is the noise, and F hat is the estimate of f of x comma y. Now comes what is this black box? Okay, because I have to make some assumption because I know I need to write some equation here in terms of f and this h. So to do that, we will make some assumptions. Okay. So the assumption I make is we will assume that this black box or this system, okay, which is going to blur the input image f and give me a blurred image here. I will assume that this has a specific property, which is linear and shift invariant property. Okay. Now at this stage, I want to ask you a question. What is an LTI system with respect to one-dimensional signal processing? What do you know by the term LTI system? Can somebody respond either through chat or through okay by unmuting? I will be happy if you unmute and speak or at least through chat. What is LTI with respect to one dimension? If you don't answer, I'll definitely take out some names. Voluntarily, if you do it, I'll be happy. Nobody want to respond? Yeah, linear time invariant. Sushma says yes, linear time invariant. Okay, so this is the expansion for LTI. What do you mean by linear time invariant system? Anybody? What do you mean by LTI system or linear time invariant system? In fact, it is there in the name itself, so you have to only expand it. No. I think Sushma, it is wrong. You cannot say varies linearly with time. That is not the correct way of explain or writing. The system satisfies linearity. Output is linear combination of individual inputs. Yes, Jaya Rohit says output is linear combination of individual inputs. Output does not depend on input. No, Sindhu, it is wrong. Output does not depend on input. You cannot say such a system as linear. It is wrong, Sindhu. Your understanding of a linear system is wrong. Output, any system output will be depending on input. Okay. What Jayarohit said, loosely speaking, it is correct. Output is linear combination of individual inputs. Okay. Or to put it in other way, the system has to satisfy linearity and the system has to satisfy time invariance. I think during signals and systems in first chapter, this is what you studied, meaning of LTI system. What do you mean by system is linear? The system has to satisfy again two properties under linearity. One is called homogeneity, other is called superposition. Okay. One is called, yeah, Pramod says output is not linear according to time. No, I think uh, linear according to time, don't bring time here, it is not correct. Okay, so let me explain. I think some of you have tried at least giving you the answers. I'm happy for it. So the system is said to be linear if it satisfies two properties. One is it should satisfy homogeneity. That means if I give f of x comma y as the input, assume that I'll get some output here, say y of x comma y. A times f of x comma y will give me the output a times y of x comma y. Okay. Any constant multiplied here with the input, the output also gets multiplied with the same constant. This is called homogeneity. Superposition means if I have f1 as the input, assume that I have y1 as the output. If I have f2 as the input, assume that I have y2 as the output. Then if input is f1 plus f2, then the corresponding output gets added, y1 plus y2. That is superposition. So if a system satisfies both both homogeneity and superposition, we say it is linear. Okay, that means some a times f1 plus b times f2 will give me a times y1 plus b times y2. I hope this was explained very well in the previous classes also. So hopefully you know that. So that is linearity. And time invariance. Can somebody tell me what is the meaning of time invariance? Quick, we have another 5 minutes left. Time invariance. Anybody? Simple, time invariance, it's there in the statement itself. What do you mean by yes, time invariant systems? No, output is not linear according to time is not the correct. Anybody? What is time invariant? When do we say a system is time invariant? Should I take some names then? If you are not. Suresh B. Suresh B.
Yes, sir.
Yeah. What do you mean by time invariant system? That is a question.
Sir, the system should be dependent on time function.
No, that is time dependence. I'm talking about time invariance. Time invariant systems. Yeah,
Sir,
Shivam says a system. Let me just read his answer. A system has time dependent, a system function that is not a direct function of time. Can you just slightly modify it? Slightly confusing definition. Okay, for want of time, maybe I'll only explain it. Any shift in the input, okay, if the system is time invariant, you will have the same shift in the output. What do I mean by that? Suppose I have say some x of t as the input. Assume that I have output as y of t. Now if I shift the input by t naught, that means x of t minus t naught, then the corresponding output gets shifted by the same shift, t minus t naught. That means y of t minus t naught. So any shift in the input the corresponding output gets shifted by the same amount in time invariant system. So somebody says output does not depend on, who is it? Let me just read out. Yeah, Jayarohit says output does not depend on absolute time. Okay. Okay. Yeah, doesn't depend on the time absolute time. It depends on the shift. Okay. So any shift in the input, the corresponding shift takes place in the output. So that is an LTI system. In image processing, you know that there is nothing like time concept, because image means it's a two-dimensional signal. So I only have the space component here, x direction and y direction. All of you know that. Okay. So I cannot say time here. I don't use time in image processing. So we use, in fact, uh, maybe the space here. That is why we call it as shift. Instead of time invariance, we call it as shift invariance. Because when I say there is a shift in the image, that means the image gets shifted in x and y direction by some value. So it is linear shift invariant. I repeat, LSI means linear shift invariant, which is same as linear time invariance in one dimension. Okay. So I hope you understood what is the meaning of linear shift invariant. So the assumption that we make for this black box, that is your degradation function, is we assume it to be linear shift invariant. Now, can anybody tell me, we have another 2 minutes, so I want an answer for this question. What is an advantage in assuming that a system is linear and time invariant? What is the advantage? What advantage we will have by making assumption that a system is LTI? Anybody? If I assume system to be LTI, what advantage I'll have? Actually, if you're carefully watching the slide here, the answer is there in the slide itself. You should put it in proper words. Anybody? When a system is LTI, or I'll put a question this way. Suppose if the system is LTI, we need to characterize it by some, okay, in fact, the term. What is it? LTI systems are characterized by what? Some type of unique response. What is that called as? Output does not depend on when an input was applied. No, if a system is LTI, I have an advantage. What is it? BIBO stability. No. Convolution. Yes, Purnima, right, you are right. So if the system is LTI, then I can obtain the response of the system for any input by performing an operation called convolution. Okay. So convolving with what? Can somebody answer? I should convolve with what? Convolve the input with what? Convolution of input with what will give me the output? Simple, straightforward question. Yes. It is, yeah, convolution with the impulse response. Yes, Purnima says impulse response. So Sumuk says impulse. Very good. So if I characterize a system as an LTI system, then I can obtain the output of the system by convolving the input with impulse response of the system. That is the advantage. So if I know the impulse response as a system, I can find the output for any input you give me. Okay, that is the advantage if the system is LTI. Very good. I'm happy that some answers are coming. So if I assume this to be linear and shift invariant, now the output here is convolution of f with the impulse response of this system. In one dimension, we use it as impulse response. In two dimension, that means in image processing, we call impulse response as point spread function. Okay. Why it is called point spread function? In the next class, I'll clarify it, because we don't have sufficient time to discuss it now. But anyway, just at this stage, think that impulse response in one dimension is actually point spread function in two dimension. Okay, so and there we used to call it as h of t because it's a function of time. Since here it is a function of space, we call it as h of x comma y. So that is the advantage. Now carefully observe, the output here is f convolved with h, where h is the impulse response, plus of course the noise that is getting added. So just see, by just making this assumption for the degradation model, I can now write the entire degradation process in the form of an equation, which is an advantage. I got an equation now. So G is f convolved with h, which is the point spread function of the degradation function, plus eta, which is the noise. Okay. Now, what are the big assumptions that we are doing? In fact, we'll discuss it again in the next class, but anyhow, we are assuming that the degradation function or this black box is linear and shift invariant. We are assuming that the noise is getting added. It is not multiplication, it is addition sign here. So noise is additive and the system is linear and shift invariant. So with this assumption, degraded image is convolution of the original image with the point spread function plus the noise. Okay, so with this we will stop at this stage. In the next class I'll clarify what is the meaning of point spread function.